In the last video, I showed you how to create a network dataset using your public transit data, and I created it using a template that just sort of magically set it up with all the desired settings. However, I think it's important that you understand what all these settings are and how they relate to public transit, because this will influence your choices and analysis and help you investigate and fix any issues you might run into. It will also help you customize your network for specific needs. In this video, I'm going to do a deep dive into the various relevant network dataset settings. The first thing to understand about a network dataset is that it has source feature classes. Source feature classes are the lines and points that actually make up the geometry of the network. For example, you could have a source feature class representing streets. You can have multiple source feature classes if you want. In our case, we'll have another source feature class representing transit lines. You can also use points as source feature classes. These are used to define how line features connect. The lines in the network are called edges and the points are called junctions. In our transit network, we'll use 3 line feature classes as sources for edges. The first is streets. This is your street data. Second is our line variant elements feature class. This is the transit line segments from the public transit data model, and this will define the public transit lines in the network. And then finally, the stop connectors. This defines small straight lines that connect the transit lines to the streets at stop locations, so travelers can transition between walking and riding transit. This is also part of the public transit data model. We will also use 2 point feature classes as junctions for the network. First is stops. That's the location of transit stops, which connect directly to line variant elements. And the second is stops on streets. That's a copy of the stops snapped to the closest street location, and this is used to ensure well-defined connections between the transit lines and the streets. Both of those are from the public transit data model. Your network will also include one other feature class for junctions. This feature class is automatically generated when you build the network dataset. It adds a point feature to each location in the network where edges connect to one another, unless you've already defined a junction in that location explicitly. This feature class is called System Junctions, and it's managed automatically for you. You don't need to do anything with it, and you should just leave it alone. Here's our network dataset in the feature dataset where we created it. Also in the feature dataset are the various source feature classes of the network dataset: line variant elements, stop connectors, stops, stops on streets, and streets, and the system junctions automatically generated feature class as well. The various tables associated with the transit data model are in the geodatabase where the feature dataset lives. The tables can't be stored in a feature dataset, so they're outside of it, but these are also in a certain way associated with the network dataset. To open the properties of the network dataset, right-click and choose Properties. There's several tabs here which have different settings associated with the network. For now, let's look at Source Settings. On the Sources subtab, we can see all of the sources that are associated with this network. So the edge sources are line variant elements, stop connectors, and streets, and the junction sources are stops, stops on streets, and the automatically generated system junctions. If you want to add or remove sources, you can click this button, and you can uncheck any of these to remove them, or if you had some other feature classes in the feature dataset that were not part of the network, you could turn those on in here. So for example, if you had an additional feature class that represented some other kind of lines, like, I don't know, sidewalks, you could add them in here. I hope you now have some understanding of how geographic data is included in the network. The next thing we need to talk about is how and under what circumstances these geographic features should be considered to connect to one another when you're modeling travel through the network. Let's start with a simple example. Suppose you have 2 street features that intersect. Should a traveler be able to transition from one street to the other at that location of intersection? What if you have a street feature and a transit line that intersect? Should they connect logically in the network or not? We can use the network dataset's connectivity policies to impose certain rules that define exactly when these intersections should represent a navigable connection. For each source feature class in your network, you can define a connectivity policy. For edge sources, that's either endpoint or any vertex. For junction sources, that's either honor or override. You can also assign each source feature class to a connectivity group to further control transitions between them. Let me explain what all of this means. I'll start with connectivity groups. When you put source features in different connectivity groups, the features won't connect to one another in the network, even if they intersect. Let's say my streets are in group 1 and my transit lines are in group 3. Even if a street and a transit line touch each other at a shared endpoint, the traveler will not be able to travel between them. In our network, we have 3 connectivity groups. One is for streets, one is for stop connectors, and one is for line variant elements, the transit lines. This is good because we don't want a traveler riding the bus to be able to magically teleport off the bus onto a street when the bus line happens to intersect that street, unless there's actually a stop there. So we use the connectivity groups to prevent undesired transitions between our edge sources. But we do want to allow some controlled connections between the streets and the transit lines. We do want travelers to be able to walk down a street and get on the bus at the bus stop. This is where junctions come in. You can put junction features in multiple connectivity groups, and by doing this, they create a sort of bridge allowing the traveler to transition from one group to another in a well-defined way at that point. In our network, we put the stops junction source in the same connectivity group as the transit lines and the stop connectors, and we put the stops on streets junction source in the same connectivity groups as the stop connectors and the streets. Travelers can now transition between connectivity groups whenever they go through stops and stops on streets. So we're using the junctions to form bridges between different connectivity groups in order to precisely control transitions between those groups. Now let me talk about how connectivity is controlled within a connectivity group. Just because 2 features in the same connectivity group intersect doesn't mean that they must or should connect to one another. It's really important here to understand how your data is constructed so you can choose the right connectivity policy. There are 2 choices for connectivity policies for network edges. Endpoint connectivity. For this policy, intersecting features must both have an endpoint in order to be considered connected in the network. If they touch anywhere else, that point of intersection is not considered connected. The other policy is any vertex connectivity. For this policy, the requirements are a little looser. Intersecting features must both have either an endpoint or a vertex at the location of intersection. The right choice really depends on the way your data is constructed. If the street features are split at every intersection, then endpoint connectivity should work for you. However, some street data is constructed with really long streets that just have junctions at intersections. You'll see this a lot with OpenStreetMap data. In this case, you'll need to use any vertex connectivity. In your network, the line variant elements and stop connectors have been specifically constructed to have endpoints at all relevant locations, so you should use endpoint connectivity for those. It's up to you to check your street data and determine the correct choice there. The tutorial data I've been using has the lines split at every intersection, so I'm using endpoint for that as well. However, depending on your data, you might need to update the streets to use any vertex connectivity. Junction sources have connectivity policies too. There are 2 choices. The first is honor. That means honor the connectivity policy of the edge sources it connects to. Override is where things get interesting. That means to override the edge source's connectivity policy. For example, if the edge source uses endpoint connectivity, features that intersect at vertices don't connect. However, if there's a junction feature there with an override policy, then they will connect, overriding the normal policy that says only endpoints should connect. In our network, we use honor for stops because they connect line variant elements and stop connectors, and they're always going to be at endpoints anyway just because of the way the public transit data model works. However, it's useful to use override for stops on streets. This way, we can make stop connectors connect to streets partway down the block without having to split the street features and without having to use any vertex connectivity for streets. The Connect Public Transit Data Model to Streets tool creates override junctions at the correct locations and adds vertices to the streets, so all of this is handled for you. Then the provided network dataset template sets up the connectivity policy the right way. We can check the connectivity settings for the network dataset in the Group Connectivity tab. So here for the edge sources and the junction sources, you can see the Groups column where the connectivity groups are defined. So streets is in group 1, stop connectors is in group 2, and line variant elements is in group 3. And you'll notice that the junctions can be in multiple groups. So the connections between the streets and the stop connectors are defined by stops on streets, and those are in groups 1 and 2, corresponding to the streets and the stop connectors. And the connections between the stop connectors and the line variant elements, groups 2 and 3, are defined using the stops feature class, which is in both of those groups. I'm using endpoint connectivity for all of the edge sources. For one of these transit networks, really the only policy that you should consider changing is for the street's source. You might want to change it to any vertex, depending on the way your street data is structured. But you shouldn't change the line variant elements and the stop connectors, because these are constructed by the transit data model, and it's set up so that these policies make sense as endpoint. You shouldn't change the Junctions connectivity policies either, again, because they're part of the transit data model, and it's been specifically constructed so that it works this way. Here I have a very simple test network in the map that I've just created because it's easier to show the structure of how things work. These purple lines are the transit lines, the line variant elements, and the gray lines are the streets. And these little lines are the stop to street connectors, or the stop connector features, and they're connecting the transit stops, which are the big purple circles, with the stops on streets that are the snapped versions of those on the streets. If I select one of the street features, you can see how at the intersection with another street is where the street feature ends. So this is an endpoint, and this is an endpoint. And at the location where the stops on street and the stop connector meet the street, this is not actually an endpoint, it's a vertex. So when I selected the feature, this entire thing got selected, but there is a vertex at this location. And the connectivity policy ensures that because of the override junction, a traveler can travel on the street and get off at that stop. And it's the same for this one. Now I solved a route layer showing how a traveler could get from this point on this side to this point on the other side. And you can see the yellow line here for the route enters the transit system at this stop location, travels along the transit line, and then gets off at this location and jumps back down to the streets in order to complete their journey. We've talked a lot about the geographic structure of the network dataset. Now I want to transition to talking about the network attributes and how travel time and distance are calculated. I'll start with impedance or cost attributes. Impedance and cost mean the same thing in this discussion, and you'll commonly see it referred to both ways. You can think of the impedance of a network edge as the cost to travel along that edge. I don't mean monetary cost, but rather the cost in whatever units of measurement are being optimized in the analysis. Usually this is time or distance. So for example, if it takes 3 minutes to walk from one end of this block to the other, the impedance is 3 minutes. Or if the block is a quarter mile long, the impedance could be 0.25 miles. Earlier, when we calculated simple walking service areas around our bus stops, we used a quarter mile as the service area cutoff. Internally, the network analysis calculation looked at the impedance of all the network edges searching outward from the starting location, that was the transit stop, and it found everything reachable within that quarter mile. You got a polygon representing the area that could be reached when the total impedance accumulated from the starting location was less than 0.25 miles. For the transit networks we're constructing, we're interested in travel time, so our impedance will have units of minutes. We calculated some service areas showing the area reachable within 30 minutes. So under the hood, the analysis calculated the time impedance for each network edge and determined what was within our time limit. The network dataset can have one or more impedance or cost attributes, and these may calculate different values. In our network, public transit time is the impedance attribute that calculates the travel time in minutes. How does the network know how to calculate the impedance? That's the job of evaluators. An evaluator is basically something that answers the question, how much does it cost to travel along this network edge at this time of day? When you run a network analysis, the algorithm searches through the network, and each time it encounters a new edge, it asks the evaluator this question. The evaluator performs some calculation and returns the result to the solver. There are several types of evaluators. The simplest is a constant. It just returns a simple constant value. We use this for our stop connectors to represent the amount of time it takes to board or exit a bus, for example. Field script evaluators are also pretty simple. They just look at the value of some field in the data and return that value. They can also do some simple calculations based on the field or use some simple logic. For our streets, it makes sense to use the shape length and apply a multiplier to convert this to a walk time based on an assumed walking speed. For the public transit lines, things are a little more complicated. The travel time along a transit line depends on the time of day. The public transit evaluator looks at the transit schedules stored in the public transit data model tables and calculates the travel time by summing the wait time until the next available transit service and the time to ride to the next stop. Naturally, we use this for the line variant elements feature class in the network. Note that you can configure the evaluators differently for each direction of travel. Let's take a look at our transit network's cost attributes. You can find them here in the Network Dataset Property pages, on the Travel Attributes page, under the Costs tab. The transit network we created from the provided template has 3 cost attributes. Let's look at length first. This is just a simple distance-based cost attribute with units of meters. You can see the name, the units, and the data type down here. The Evaluators section shows how the length attribute is calculated. This is where you can view and configure the evaluators. Note that here in the data grid, there's a section for edges and a section for junctions. If your network had turns, there'd be a section for turns as well. Each edge source in the network shows up twice in the edges section, and there's an entry for along and against, so you can configure the evaluator differently for each direction of travel. For junctions, there's only one of each because they're points. For the length attribute, all edges are configured to use a field script evaluator, and they're using the shape field to get the distance of the edge. Let's look at the cost attribute called walk time. This attribute is intended to calculate how much time the traveler has spent walking while they're going from one place to another. In the evaluator section, you can see that the walk time is 0 for line variant elements and stop connectors. That's because the traveler is assumed to be riding transit, so they aren't walking. For the streets, they're using a function evaluator. It's a function of the length attribute that we just looked at, divided by the walk speed. The walk speed used here is an attribute parameter. It's defined here in this parameters section, and its default value is 83.3 meters per minute, which is approximately 3 miles an hour. I'll show you a bit later how you can use this. Let's finally look at the public transit time attribute. This is the primary one we'll use when we're solving network analyses because this is the one that incorporates the public transit schedules. Line variant elements is using the public transit evaluator. This is the thing that queries the public transit schedules. Streets are using a function evaluator, and they're just multiplying the walk time attribute by 1. So remember, we looked at walk time a moment ago, and that was calculated based on the length of the street and the assumed walk speed. And so for a public transit calculation, when we're considering a street, it's just calculating using the walk time, but when we're considering a transit line, it's using the public transit data. Stop connectors are set to 0, so there's no additional time incurred to model boarding and exiting the transit vehicle. If you wanted to, you could set this to a different constant value to model a delay for every boarding and alighting. Or if you had some data about subway stations and how long it takes to walk from the platform to the street, you could put that in a field in the data and then use a field script evaluator for that. Restriction attributes are used to prevent travel on edges with certain characteristics. For example, you might want to prevent pedestrians from walking on highways. Restriction attributes are just like impedance attributes in that they're configured with evaluators and they can use attribute parameters. If your highways are defined using some specific road class field, you could configure a restriction attribute with a field evaluator that checks the road class and sets the restricted status equal to true for any road class value that pedestrians shouldn't be on. In our network, the provided template creates 2 restriction attributes. Pedestrian restriction prevents pedestrians from traveling on roads where they're not allowed, such as highways. Wheelchair restriction prevents travelers from taking roads or using transit stops that are not wheelchair accessible. Attribute parameters are used to modify the behavior of a network attribute at analysis time. It's a way to update some settings without having to modify the network and rebuild it. For example, you could configure a walk speed parameter that can be set at solve time, which modifies the impedance along street features. This isn't really pertinent to our current analysis, but it serves as a good, clear example of attribute parameters. Let's say you have a network designed to model truck driving. You might configure a restriction attribute to restrict travel under low bridges if you're driving a tall truck. The size of the truck you're driving might change, so you can enter the truck height as a parameter at solve time, and the restriction attribute will just do its job and prevent travel under low bridges if necessary, given the size of the truck. Most of the time, the parameter names and values are defined by the person creating the network. However, the public transit evaluator is a bit special, and it has several parameters it can use if you set them up with the correct name and data type. You can use the exclude lines, exclude modes, and exclude runs parameters to prevent travel on certain lines using specific runs or using particular transit modes. This is valuable if you're experimenting with a couple of different scenarios, and you can turn off service for those scenarios. You can also use the traveling with a bicycle and traveling with a wheelchair parameters to indicate whether the traveler is traveling with a bicycle or wheelchair. This is kind of a non-standard use for attribute parameters generally, but it actually works really nicely, and I refer you to the documentation for details on how to use them. So far, we've talked about cost attributes, restrictions, and attribute parameters. Your network dataset can have more than one of all of those, so you can model multiple things. But for a specific analysis, you only want to use some of these, or you want to configure them specifically for the analysis you're doing. For example, you probably want to use a specific cost attribute and apply some subset of your restrictions, and you might want to set the attribute parameters to model the specific non-default characteristics of whatever situation you're modeling. This is why we have travel modes. A travel mode represents a collection of network dataset settings that can be applied for an analysis. Travel modes usually represent a particular mode of travel, such as pedestrians walking and taking transit. The network dataset we created earlier from the provided template has two travel modes, public transit time and public transit time with wheelchair. You might want to create some additional travel modes, like one that models service cuts along a particular line and makes use of the exclude runs parameter. Just like cost attributes, restrictions and travel modes can both be found on the network dataset property pages under the travel attributes page. Here's the restrictions on our network dataset. We have pedestrian restriction and wheelchair restriction, like I talked about in the slides. And these are both configured with evaluators. Here's travel modes. By default, the network has two travel modes, public transit time and public transit time with wheelchair. You could add more of these for your own specific circumstances as you need to. Let's take a look at my simple test network and the simple route analysis I did with it. For this route, I used the public transit time travel mode, which uses the public transit time cost attribute under the hood. Remember, a travel mode is a collection of other settings, including the cost attribute to use, the restrictions to apply, and any attribute parameter values you want to set to something other than their defaults. This route is optimizing the public transit travel time through the network. It's going to find the fastest way to get from point 1 to point 2 according to the public transit time cost attribute. Another interesting thing I did with this route was to accumulate the walk time attribute. When I solve the route, it will optimize according to public transit time, but the results will tell me how much walk time was incurred during the journey. Let's take a look at the travel time calculated for this route. I'll open the attribute table. And if I scroll over here, the total public transit time field is telling me the total travel time for this route. And it's about 6.8 minutes. And this includes both the walking time and the riding time on public transit, and any wait time the traveler needs to wait for the bus to arrive. The total walk time field is showing the accumulated walk time attribute value for this journey. And you can see that it's about half a minute. And that's because it's only these little segments on the end where the traveler was walking. And remember, the way we configured the walk time attribute was that the stop connectors and the transit lines have a value of 0 for walk time. So that means that of the 6.8 minutes for this total travel time, about half a minute was walking. Let's talk about attribute parameters. Let me open up my travel mode settings here so we can see the details. I'll expand this so we can see it a little bit better. Here in the cost section, we have the walk time parameter, and you can see that right now the walk time for this travel mode is set to the 83.3 meters per minute, which was also the default value of this parameter on the walk time cost attribute. But I can override that default value and set this to something else. Let's say that we have an exceptionally speedy walker, and they're going to walk at 200 meters per minute. I can set this value here, and now I'm using a customized travel mode for this particular route analysis, and I'll solve again, and you'll see I'll get a different result. Okay, now the optimal journey from point 1 to point 2 is actually just to walk along the streets, because in this case, our exceptionally speedy traveler is actually walking faster than the bus is driving. So for this traveler, it's faster to walk. You can see this in the route attribute table as well. Now the total public transit time, which is the cost attribute that was optimized for this analysis, is about 3.6 minutes. And it's the same value as total walk time because the entire journey was spent walking and there was no riding involved. Now the total time for this route is still reported in this total underscore public transit time field because this is still the cost attribute that we're optimizing. Even though the traveler was walking the whole time, it was still this cost attribute, so this is the field that we want to look at. Let me reset the travel mode back to the network's default and solve again. Okay, we're back to the optimal route using the transit line like we had before. Now let's look at the special attribute parameters recognized by the public transit evaluator. I'll open my layer properties again. Now the public transit time cost attribute has a series of attribute parameters that are associated with the public transit evaluator. Let's just play with this one for now, exclude lines. And I'm going to tell it to exclude the line with ID 1. Now I'll solve again. And now the optimal route has switched back again to walking the entire journey. And that's because this public transit line is associated with line ID 1. And because we excluded that from the analysis, this traveler can't use that line. Looking at our routes attribute table, the total public transit time is about 8.7 minutes, which is longer than the transit journey of 6.8 minutes that we had earlier. But because that line is no longer available, this is the optimal travel time. For this example, I've been showing you how you can change your travel mode settings on the fly for a particular network analysis layer in the map. That's what I've been doing when I've been clicking this launcher button and changing the layer properties. However, if you're going to do any serious analysis and you want some of these special settings, you might want to make some additional permanent travel modes on your network dataset. You can do this using the network dataset properties like we were looking at earlier. So on the Travel Attributes page in the Travel Modes tab, I can create a new travel mode, and let's call this Public Transit Time with Fast Walker and Line 1 Excluded. That's a very long name for a travel mode, but it'll work. So by default, this travel mode has selected the public transit time impedance attribute. That's good, that's what we want. And there's some restrictions applied. I could change these if I wanted to, but what I care about for now is the parameters. So I'll override the default value of the walk time parameter, or the walk speed parameter, change it to 200. And I'll override the default value of nothing for exclude lines, and I'll exclude line 1. Now I can click OK. And this travel mode has been added to my network. With this new travel mode on my network dataset, I now have this option to select from the travel mode picker for an analysis layer. So you can see here public transit time with fast walker and line 1 excluded that I added a moment ago. And I could choose this and it would have those settings that I applied when I added the travel mode to the network dataset.